All right, so we've got a way of thinking about vectors geometrically. We can imagine these things in two-dimensional, three-dimensional space. And we're going to talk about a couple descriptors of these things. When I say descriptors, just a word to describe certain features of our vectors. So we're going to start with the descriptor of norm. So this notion of norm is going to correspond to our standard geometric notion of length. I put the length in quotes because when you eventually get out to 4 and 5 dimensions, length is sort of more of a nebulous concept because, well, I mean, how long is something when it's out in space at a dimension that you can't see? Well, in order to sort of capture that notion of length at the higher dimensions, rather than calling length, we call it norm up in those higher dimensions. So norm is just a generalized notion of length. And well, let's sort of see this so that we can imagine how we can compute norm. Oh, I should make a remark before I proceed here. Norm, notation. Whenever we talk about the norm of a vector, in other words, the length of that vector, we're going to use 2 vertical bars to describe that. So I know you may be used to seeing like 1 vertical bar for absolute value. Here we're going to use 2 vertical bars, where 2 vertical bars around a vector is referring to the norm of that vector, which is in effect the length of that vector. So let's see, let's sort of develop a notion of norm through using the 2 and the 3-dimensional case to sort of see norm in action, to see length in action, to see how we can generalize norm to n dimensions. So let's do the example like 2, 5. So let's take this vector 2, 5, and what we want to find out is what is the length of this vector. So we are going to find the length of this vector. And what does this vector look like? Well, as you know, the first letter is corresponding to the x position and the second to the y. So 2 units to the right, 5 units up. There is a vector there. We could call that vector by whatever name we wanted. I guess in this case, let's just call this vector A. So we want to find the length of vector A. And now when you think about this, you know that the x movement horizontally and the y movement vertically is perpendicular to one another. And by virtue of that, then, you've got a right triangle here, which you could apply the Pythagorean theorem to. So if you want to know the length of the vector relates to Pythagoras, right? Because the length squared of the hypotenuse would be equal to what? The sum of the squares of the other 2 sides. So in the case of our vector here, its norm squared is 2 squared plus 5 squared. In other words, its norm is the square root of 2 squared plus 5 squared. That's the length of that vector. And if you want to generalize this in your mind's eye, you could say, okay, well, what if our vector was not just 2, 5, but any a1, a2? Well, in that case, the vector would be a1 units to the right and a2 units to the left, or excuse me, a2 units up or down. And the long story short is whenever you consider that 2 to be any a1 and that 5 to be any a2, you would have a notion of norm, a notion of length in 2 dimensions as such. And now here's the question. How would this notion manifest in 3 dimensions?